I'm really pleased to be sharing some knowledge at this school, and it's great to be here. I'm a little bit jet lagged, so if I stumble over my words, we'll blame it on that. But yeah, so I'm going to be talking about how we can use FORCAST to determine stellar properties. So for those of you who don't know, FORCAST is the Faint Object Infrared Camera for the SOFIA telescope, and it covers a wavelength range between about 5 to 40 microns, which is particularly useful for the type of stars I look at. So I look at red supergiants, which emit a lot of their light in the infrared. And there's a short wavelength camera and a long wavelength camera. And the cool thing about this instrument is you can use two channels at once. You can use a short wavelength and a long wavelength at the same time. So you can get two sets of data for the price of one. So it's a really cool instrument. And the data is really good because it generally comes fully reduced, including flux calibration. So I haven't had to worry too much about any of that, which is obviously really good for me. But if you are interested in reading about it, there is a really good data reduction tutorial at the SOFIA website just there. But this is what the sort of data you get looks like. So on the left, there's a 3-color image of the cluster Westerlin 1. So these bright points here are the red giants, which are the ones that I look at. You can see when we have 3 sets of photometry, so we've got short wavelength 5.6, we've got 11.1 microns and 25.3. When you stack them all, you can sort of see what's going on with the stars. So you can see there's a star in the center, and then there's a lot of emission around the star. So you get a lot of information. So we can see, rather than just seeing the stars as a point, we can see the sort of structure. In this case, what we're seeing is dust emission around the star. But if we look in one wavelength, this is the sort of thing that the data looks like. So this is the FORCAST 5.6 micron channel. And again, the red supergiants are these big bright stars. So they're really, really bright at these wavelengths. And those are the objects that I'm mostly interested in. So you get your data, and if you're looking at a cluster like this, where the stars are really well separated, you can use aperture photometry to get your fluxes out for each star. So I use IDL, so I use something called Starfinder or DALFOT, which I think works outside of IDL as well. Or you can use one like this, which is more visual. So it's Gaia Starlink. So that's what this is over here. So you can load up your image in whichever wavelength you're looking at, and because it's all flux calibrated, it's really simple to get the data out from the image. So you simply draw your aperture around the star. And then there are rings surrounding this central aperture. So you've got to try and get all of the light from the star in this middle one. And then you have extra rings around which cover the background, and you've got to make sure there's no other stars within these rings contributing to the flux, so that you can do a nice clean background subtraction from your data. And pretty much since it's flux calibrated, you can just read off the flux for that wavelength, and you can do it by hand, or you can kind of automate this, as I said, through whichever coding software you use. You probably use Python, and you can just do it really simply. So the data from FORCAST comes ready to go, so you can get straight down to it with the science. And for me, the important thing is determining stellar properties. So I look at massive stars, and knowing what goes on with massive stars helps us understand which stars explode and which ones don't. So massive stars are those with initial masses between about 8 to 25, 8 to 30 solar masses. And it's kind of a little uncertain where the upper end is to which of these stars explode and which ones perhaps don't explode. Maybe they fail to explode as supernovae and collapse as black holes. So to know which ones are exploding, it's essential that we have their luminosities, which is how we get their initial masses. So a place where this shows up in particular is when you see a supernova, people go back through the archival imaging and they try to identify a potential progenitor. So in this middle image here, you can see the supernova, and then you can go back through the archive and look in the location where the supernova went off and try and identify a progenitor star. So you can see here in figure A. And then you wait for the supernova to fade away, and you can go back and you can confirm whether or not that was the star that exploded. And in this case, you can see very clearly that this red star that was in figure A has now disappeared. So that we can be pretty confident that that was the star that exploded. Now, in this case, the photometry is clearly more than one. It's clearly more than one wave band because you can see its color images in the pre and the post explosion imaging. So we have a pretty good idea of what this star looked like. So you can see it's quite red. But for most cases, you actually would probably only have a single wavelength to go off. So you have to make some assumptions then. You can get a flux out from that and work out a magnitude at that wavelength. But what we're interested in is knowing the bolometric luminosity, so the total luminosity across all wavelengths, so that we really know how intrinsically bright the star is. So it's not completely hopeless if you only have one image, if you only have one waveband of information, you can get a bolometric luminosity out. So bolometric magnitude is the magnitude, as I said, when you integrate across all of the wavelengths. So you can see the total intrinsic flux coming out from the star. So then if you have one image, you have a magnitude at that given wavelength. So before I showed the 5.6 imaging for the SOFIA photometry. So suppose you had a star and you'd only imaged it in that one wavelength. Well, there's something called a bolometric correction, which corresponds to that wavelength. So for a given wavelength, you can use a bolometric correction, which is calibrated for that wavelength, and you can determine a bolometric magnitude. So it's a little uncertain because you're making a big assumption about the color of the star, and then eventually you can get the luminosity out using this equation at the bottom. But this bolometric correction, as I said, like depending on the color of the star, you need quite a different, you might need a completely different bolometric correction. So in this top left-hand panel, we show how the bolometric correction for a V-band observation varies with spectral type, but you can think of this as decreasing temperature. So the further along the x-axis you go, it's like you're going down in temperature. So if you had a star and you assumed it was, so this is for red supergiant specifically, suppose you assumed it was quite a warm red supergiant, well then you would need a bolometric correction sort of around here between spectral type 0 and 2. But if it turns out it's actually more evolved, it's actually a cooler star, then what you actually should have used was the bolometric correction from all the way down here. So you can see that there's quite a big difference between that. So the V-band correction here is about -5, whereas up here it's about -1.3. So depending on what you assume, you could end up with a different luminosity by perhaps 0.5 dex or so, which is a big difference when you're trying to work out how massive and how bright these stars are. But for each waveband, there are different bolometric corrections. So this is the how the bolometric correction in the R band changes as you go along spectral type. So you can see there's again quite a big difference. But the best ones to use for a red supergiant are the K band. If you have K band imaging, then you're going to get a more reliable luminosity out, just because the bolometric correction doesn't really vary that much as you go across spectral type or temperature. So it's almost kind of flat. It doesn't vary a massive amount. So even if between the min and the max, like you're not going to end up with a hugely different luminosity. So if you only have one photometric point, then you can get a luminosity out, but you have to bear in mind that you have to make an assumption about what the star looks like before you even go into it. But in some cases, you might have, so for these supernova progenitors, sometimes they have 2 detections. So you think that's great, it's more than one, so then you know the color of the star, so you've got a little bit more information to go off. You might know how red it is, for example. So you need to then fit a model to it. You are still kind of assuming a temperature. So you might assume that the model looks something like this. And it kind of looks like it would really match the photometry you have there. But in reality, the star might peak more in the blue and look something like this. And if that's the case, then you've missed all of this flux here, which is contributing to the luminosity. So you've actually still missed quite a big chunk of the flux that's being emitted by the star. And this can go the other way as well. So suppose you fit your model like this, the star might also be emitting at a longer wavelength. So these stars are quite dusty and they can emit at longer wavelengths. I'll come back to this in a little bit. And if you've just assumed a star with no dust or assumed a certain temperature, then you're still going to miss quite a lot of flux. So even with just a couple of points, you can get a better handle on what the color is, but you might still end up missing flux, which is, as I said, important if we need to know the total luminosity. So by far the best thing to have when you're trying to work out a luminosity of a star is as complete an SED as possible. So we've got wavelength along the X here and then flux along the Y. And this is what the SEDs for the 4 red supergiants in Westerland 1 looked like before we had SOFIA data. So you can see we only have photometry going up to one or about 2 point something. I think it's like 2.2 microns. So we don't really know what's going on with the flux beyond there. And you can use, so this is K band here. So you could use a bolometric correction of this and try and get a luminosity out. You could fit models here, but you are making big guesses about what's going on in this section of the SED. So the reason that it's been so difficult to get parameters out for these red supergiants is that the photometry that was available, it was super saturated. So Westerland 1's a really nearby cluster. So the Spitzer and Weiss photometry that was available was just saturated and unusable, so we couldn't do anything with it. So there was, until we got FORCAST data, there was no way to get luminosities out in a reliable way. But then we managed to get SOFIA data, which covers this section of the SED, and you can see how much difference that makes. So you didn't really know what was going on over here, but you can see that some of the stars have more emission down here at the longer wavelengths, and this one has almost no emission. So it's really important that we fill in the SED, and then once we have done that, you have to correct the photometry you have for extinction and for the distance. So this is just an extreme example. This is one of the stars. This is the SED for W20. So this is just as we see it, but we need to correct this for the extinction that is in front of the star or within the cluster, so for any dust that's in the way. And the way you do this is you take an extinction law. So along the bottom we have the wavelength, and then along the Y we have the extinction coefficient. So this just tells you how much extinction affects each at the flux at each wavelength. So this is A lambda over AK. So you simply need to know an extinction value for this particular law. We need it in the K band, and then you can sort of multiply the SED you see here by the extinction law, and then you can see what the star would actually look like if there was no dust in the way. And this isn't the best fit model. This is just an extreme example to show you what that can look like. So over here we have the SED that we actually see in the sort of blue dashed lines. I know it's not extremely clear. And then you apply the extinction law I showed here, and the flux of the star now peaks around here, and a luminosity out you have to integrate under the entirety of the SED. And in this case, we didn't have any data at the shortest wavelength, so we used the black body to fill in the gap. So luckily for this section, we used the black body to fill in the gap, but we assumed a temperature and sort of varied it by plus minus 1,000 Kelvin to make sure it didn't have a huge impact on our results. So what you basically do is integrate under the SED, and the flux wavelength, the area of the flux in the wavelength gives you a luminosity, and you need to times that by the area of the sphere to get the total intrinsic luminosity of the star. So to do this, I use an IDL function called intertabulated, but you can of course do it in Python or whatever coding language you use. And then you scale it to the distance of the star. So these stars are quite nearby. I think they're like 4 kiloparsecs away. So you end up with a luminosity for the star that is correct to the distance. And the main sources of error here are the distance and the extinction to the star. So particularly for Westerland 1, there's a lot of extinction in the way. So it's a Milky Way cluster, and there's loads and loads of dust in the way. And the distance is actually really hard to measure as well, but it has got a lot more reliable with the release of Gaia. So I will really quickly talk to you about Westerlin 1 and why I think it's a really cool cluster and why it's worth knowing about what's going on. So this cluster is, yeah, as I said, a nearby Milky Way cluster, and it actually contains a whole host of massive stars. So, sorry, it's got red supergiants, it's got yellow supergiants, blue supergiants, Wolf-Rayet stars, it's got a magnetar, and it's really unusual to see all of these stars coexisting, just because the lifetime for example, Wolf-Rayet is so short, and the lifetime for red supergiants is quite a bit longer. You wouldn't expect to see them existing at the same time. And so a lot of people thought that Westerlin 1 was an example of a starburst cluster. And the reason that this is really cool is that it's the only one where you can actually resolve all of the stars within the cluster. So this is what a starburst galaxy usually looks like. So you can see it's just sort of a smudge. And you can still learn a lot about the galaxies from this, but you need to know like kind of what colors you're expecting. And so Westerlin 1 is kind of like a Rosetta Stone for understanding these clusters where we can't actually resolve anything just based off the colors. Yeah, so it's got extreme stellar diversity, which makes it really interesting. And there's no other cluster like this that we know of. And yeah, so as I said, it's really hard for all of these stars to coexist, and under the single star paradigm, only a very, very specific age could explain both the red supergiants and the Wolf-Rayets coexisting. And this led Clark in 2005 to suggest an age of 5 megayears, which would imply all of the stars within this were above 30 solar masses. So they would be really, really massive red supergiants. I think maybe the most massive that we know of. And this would make Westerlin 1 also the first example of a superstar cluster in the Milky Way with a total mass of around 10 to the 5 solar masses, which would make it the most massive galactic cluster yet discovered. But with the 5 megayear age, we have a good prediction of how massive these stars should be. We also know kind of how bright the red supergiants should be. So it's really simple to test this. So using the total FCDs that I showed you before, we worked out the luminosities for all of the red and yellow supergiants within the cluster. And so these are the red supergiants here, the red dots, these are the yellow hypergiants, and then these are all the Wolf-Rayets. And just to show you, to put it into context, this, sorry, gone the wrong way. This is the isochrone for the age that people thought Westerlin 1 was. So people thought it was around 5 megayears. But you can see that looking at the red and the yellow supergiants, they're nowhere near bright enough for that to make sense. So what we instead suggested was that perhaps the cluster was older, or perhaps it was influenced by binary interaction, which can make stars live longer and make stars appear older. Or perhaps there was like a multiple periods of star formation. So maybe all of these bright Wolf-Rayet stars formed at an earlier time, and then that these formed at an earlier time, and then there was another burst of star formation with these younger objects. So that's one cool thing you can do. So this would sort of take away Westerlin 1's status as the most massive galactic cluster that we know of, if correct. But what's clear from this is that just by seeing the luminosities of the red supergiants, it cannot be a simple 5 megayear like starburst cluster. So that paradigm just does not make sense anymore. So that's a pretty cool thing that we've done with SOFIA data. Another application is to look at the mass loss rate. So just ignore this grey blob for now. So I won't go into too much detail on this, but if you have a star, this is how it emits flux. But if the star is surrounded by a layer of dust, then flux gets absorbed over here, and it gets re-emitted at longer wavelengths down here. And the shape of this bump here tells you about the dust composition. So for red supergiants, it's silicate-rich dust, which is why you end up with this bump here. So if you want to know about mass loss rates, or the sort of dust structure of these cool stars, then you need you need data that is covering this section of the SED. And again, this is another thing that SOFIA is perfect for. So this is more SOFIA data that we had. So this was for a paper in 2020. This is all SOFIA data over here. And we use the data and we match it to models, so to dust shell models. So in this case, we use called DUSTY, which is a radiative transfer code. So it works out what a spectrum of a star would look like if it was absorbed by dust of, you know, a certain optical depth, a certain inner dust temperature, a certain a dust composition, and then you can find a best fit model, and from this you can derive a mass loss rate for each star. But one important thing to note is if you want to do the sort of modeling where you sort of match these synthetic models with the data, it's important to note that the SOFIA photometry, or in fact all photometry, doesn't emit as like a flat box across the wavelength. So if you want to compare directly the model photometry with the real photometry, then you need to convolve your model photometry across these sort of filter profiles. And a really useful service is the SVO filter profile service, which is, you can just Google it. It has all of the filter profiles for pretty much every telescope in the world, so you can convolve your data and get a better match. So I think I'm coming to the end now, and I was asked to prepare a slide on giving advice to infrared astronomers, and I think these are the things that I learned most in proposing for time and things. So I think when you want to propose for telescope time, you should always come at it from the science perspective. Like, I think some people go into proposing for telescope time thinking, oh, I need to put a proposal in, but it should always come from having a good science idea and figuring out what observations you need to make that science happen, or to answer the question you want to answer. Always ask people to read your proposals. So most postdocs and faculty will have served on some sort of panel themselves, be it like a telescope panel or a grants panel. And in doing this, you learn what makes like a proposal good and what panels tend to like, and how to like really sell your case. So just getting people to read over things is useful. I know that since I've been serving on the occasional panel, like my proposals, like I feel much more confident writing them. Another one is don't be put off by negative reports, whether it be on a paper or for telescope time. It can be very frustrating if you feel that it's a bit negative, but it just shows you the ways that you can sort of make your paper really bulletproof, and how you can make it like super strong so that there's like no question that your results are really solid, and that you're really upfront with all of your assumptions and things like that. And finally, I think it's important to just remember like how cool our job is. Like, I think sometimes everyone can get bogged down with like, you know, endless coding and writing, and it can be, you know, there's things like that which can be a little bit tedious. But, you know, when you think about it, we're using, for example, a telescope that's strapped to the back of a plane, which I think is pretty cool. So yeah, so just keep up the enthusiasm and just remember how cool it is when you're feeling a bit off with it. But yeah, I will leave it there.